So today, see if you can hear me. Here is how we are going to split our time. I'm going to make to go over conduction currents, which we did not cover last time, to the extent that you have seen in my notes. And then we're going to have two quizzes. I will give, so the group quiz is going to be first. And it's going to be, we'll start around 2:40, 2:45. It will be half an hour. We'll take a break. And maybe we can take the break before, if I'm done with this, before we go to both quizzes. But I would suggest that we take the break in between. So half an hour for the group quiz and half an hour for the individual quiz. Okay, so I will, on materials that you have seen before, it does not include conduction currents. If you just worry about that, obviously we did not cover the material enough or at all practically to have it in the quiz. And that's how we are going to do this. So everything open, everything, you can use everything. Open notes, open books, your laptops. When you work with your group, that's fine. Keep your voices a little lower so it does not become too noisy in here when you collaborate to solve your problem. I would like the group leader to bring the problem for the group here. So we are going to collect 20 group solutions from each group one. But I'm going to give to each one of you a copy of the group problem. So each one of you has it in front of you, all right? But I need one to come back to us. And then the individual will be each one of you individually. Then, of course, I would like you to do the work by yourselves. All right. Let me start with conduction currents and then talk a little more about where we use those conductive materials. I just want to summarize for you how we are building our understanding of electrostatics using different types of materials. We've started, therefore, in chapter 1 in the book with electric fields and they were in free space, as we call it. Sometimes you will see you call it air. So free space is a medium that is neutral. If there is a charge in there, then it generates a field. If there is no charge in there, there are no fields. If you have one charge and generates a field, and then you bring another charge, then the second charge is going to feel a force, but only from the original charge in the medium. The medium by itself does not interfere, does not produce other charges, does not produce other fields. It's pretty neutral, all right? So this is a neutral then medium. While we were with that and we brought charges in the medium, then we started adding conductors. And in fact, perfect conductors. So from this, we went to perfect conductors. And then in there, we assumed that there are a lot of electrons that flow around. And as a matter of fact, they flow so fast under the influence of an electric field that they will separate from their own nucleus. So they will leave their atoms positively charged, and then they will go into places on the basis of the electric field that has been exerted. If there is no electric field, of course, none of this happens. And so in a perfect conductor, you just have all of these free electrons, and they only start grouping together when there is an electric field. And what we assumed in there that the electric field inside this conductor is 0. all right? Then we went from perfect conductors to perfect dielectrics. What does it mean? A dielectric that is uniform, that is linear, and that does not have losses. And so in these dielectrics, we spoke about not free electrons, but we spoke about bound electrons, as sometimes you will hear it, which means that the electrons do not necessarily leave the nucleus, but they are displaced within the atom. All right, so if without an electric field, everything is balanced, so you have the center, the charge here, and all of the electrons just in a very balanced way orbiting around, if you want to use that simple model, giving a zero charge. Under the influence of an electric field, this picture changes. So with an electric field, these now atoms, the nucleus is still positive, but if the electric field comes like that, and so forth, all of the negative charges will accumulate here, at least those that they were in the outer levels, all right, of this atom, and then fewer of those will be here. What does that do? That displaces the center of the negative charge from the center of the positive charge and creates a dipole. And we said this sometimes we indicate it like that. And then we characterize this dipole by the dipole moment. All right, if this is a point charge Q minus Q and the distance is D, dipole moment was P, in fact M, excuse me, for that, D, Q. And then that adds its own field. When you put a dielectric into, for example, a capacitor, we said that the electric, because it creates this its own field, tends to reduce the electric field inside the capacitor. All right, so that's its impact. Now we are moving from dielectrics and we are going to a new type of material, the conductors, not the perfect conductors, but conductors. And why are we doing that? Because now we are building our knowledge around what happens to electric fields starting from a very simple medium to different other media until we go to something that has all of the above. All right, has dipole moments, has free electrons, and so forth. So in a conductor, which is not perfect, all right, so that is just to remember where we've been and how we came here. You don't have, as in a perfect conductor, all of the electrons free to flow. In a conductor, and we show a conductor, you can show a conductor like this, or like a rod. Let's assume that you have this conductor here. You have many free electrons, but not all of them. So what happens inside a conducting medium, the electric field is not zero. All right? The electrons do not go to the surface as it happened with metals and perfect conductors, but they stay inside and then under the influence of an electric field. And let's assume that here we had, as we said, positive charges, or in fact, if you like to do it like this, we had a positive charge here. We had a negative charge here. And the electric field lines will go like this, which means then that the electrons will move this way, and the positive charges will move this way. And whenever positive charges move, that's the direction of the current that we say, because practically, in a medium like this, you have charges leaving the volume. All right, the charges are leaving the volume. And the charges are moving with the velocity. So what happens to the charge in here, the charge changes. So if you take its, if you measure it at every point in time, and then you can take its derivative, you will see that there is going to be a growth of the charge inside or a reduction of the charge inside. And this microscopic view, which is also very conventional, we try to show that phenomenon for this kind of material. All right, the two metals on the side are primarily to create that electric field. And since there is a flow of charges out of the volume, then we show this here with a current, I. And this is a total current. And it's measured in amps. The total current practically takes into account all of the electrons that are moving, or in fact, in this particular case, the positive charges, all right, because we go along this direction, the direction of the positive charges. But the total current takes into consideration the movement of all of those charges. So it's not a density, all right? It comes as the result of current densities, which in fact, very simplistically, you can assume. If I put here a positive charge on this plate, and then negative on here, I will force all of the charges to move. And simplistically, you can say, well, what if I have a point charge here, positive, which moves? And then this is going to move, ideally, like this. And eventually, it's going to be collected by this metal, which means, or it's going to mean collected, it's going to be there, which means that there is charges that will leave the volume. So eventually, it will be collected by a source if the metal is connected to a source. And then more charges will come in. All right, so there is a flow. So if you assume, you make a hypothesis that you can watch this movement or this trajectory of the charge, then there will be many of them like this. And it is the sum of all of those that will give the total current I. So from that current I, then we can go to the definition of a current density. And this particular current density that you see here is going to be a surface current density. Meaning, if it's measured in amps, this is going to be measured in amps per surface, unit surface. And why is that? Because if I could look at this surface here, let's assume that I go from here and I look at it, what I see, all right, on this space, is I see all of these lines that are representing the trajectories of all of these charges and practically showing positive charges that there is a current that is flowing out like this. And this current is, to give the total, it has to be integrated over the surface, and that's why this is a surface current density. All right? So that what we know from macroscopic analysis is that J, and in fact, in this particular case, people may show it as J sub S, or sometimes when we speak about that charge density, sometimes we drop the S. But for now, I will keep it So at least we remember the units. So total I, therefore, if we assume that all of these individual current densities are uniformly distributed, then it's going to be what? The surface integral on this surface S. This is surface S. And we always said that surfaces, when we integrate, have a direction. So a lot of times we show surfaces like vectors. And if we show a surface like that as a vector, its direction is going to be perpendicular to the surface, all right? And that's going to be n. So the vector for this surface S is going to be perpendicular, or here, if you want to show it here, it's going to look like this. So practically, this comes to be the S surface of J ds. And if this is uniform, it's going to be J sub S, the area, where this is the area or the cross-section. Now, what you can find from a microscopic analysis and then go into a macroscopic convention is that J sub S is nothing else but is proportional to the electric field. So, and of course that's the case, because what happens if we assume that J shows the trajectory of one charge, all right, and if the charge is inside this electric field, well, the charge, of course, is going to move under the presence of a force along the field lines, all right? So it makes sense for these two to be parallel, and of course their value now it changes. So the value of the surface charge density is proportional to the electric field intensity by this parameter sigma, which we call the conductivity of the medium. And for ideal cases, we assume that this conductivity is uniform, all right? So sigma is conductivity. And the word literally means it's a constant that shows how many of these positive charges or electrons this medium can provide that can flow through. All right, so now we will come with some other definitions. Let's assume that we have a voltage V. All right, so we supply positive charges here. We pick the negative charges from there. And so across this, what we now call a resistor, you will see when we will, of course, we call it conductor up to some point, and eventually we'll define a parameter that is called resistance, and we will call it a resistor. So we are going to find that total I is sigma A, and then the electric field E. And then we also know simplistically that this voltage between these points 1.1 and 2, this voltage is nothing else but the integral, if you remember, of V dot dl. And practically, this is going to give nothing else but the, and then that should have been 1 and 2, and then 2 and 1, and that's nothing else but minus EL, where L is the length of this. And then I will practically come to talk to you about this negative sign. So you will see, because you see something that is different from what you have seen in circuits for resistors, all right? Now, this voltage difference is measured from this point to that point. And that's why it's given, has a negative sign here. So I will continue for a moment, and then you will see why the negative sign is not a mistake in this particular case, especially as we go to circuits. So we have V and we have I. So V is the voltage difference between these 2 points from V1 minus V2. That's what it shows, V1 minus V2. And I is the current that goes through. We know from circuits that there is a parameter R, which is V over I, and that is the ratio of the voltage across an element divided by the current that goes through. This is the resistor. When we, in circuits, show a resistor like this, and then show practically the voltage between point 1 as V and point 2 as V, this V here across the resistor is, and let me call it V resistor. V resistor is nothing else but if this is point 2 and this is point 1, V2 minus V1, okay? That's why the negative sign is right, because coming from the electrostatic equations, going to circuit equations, we had here as the voltage drop between points 1 and 2, V1 minus V2, which is there. But going into circuits, V sub R will be EL, all right, according to this definition. And therefore, R will be EL divided by the current, which is sigma E A, according to that. Is JS, which is sigma E, times the area A. And therefore, what you find for the resistance of this simplistic and ideal element is that it's equal to the length divided by the conductivity times the area. Yes?
Where's the current flowing from on the resistor?
Okay. Yes. Yes. And so conductivity, what your colleague said is, you can take 1 over sigma and define yet a new parameter. All right, so the sigma is called the conductivity. For a moment, let me keep this. There's that. And I will keep that. When you look at this, R is L over sigma A. What does that really tell you? It says that the more the electrons you have that can start moving in the medium, then the higher the resistance to the current that this device shows. And why is that? Because as you increase the number of electrons, then all of these electrons, they are not necessarily going as nice as this one, all right? Because this medium, it does not just have electrons, the medium has a structure, which means that there are all of these atoms in different positions, and the electrons, as they try to go through, we say they reflect some ways. You could say they reflect off another atom, or they, as they try to go through an environment where there is an atom and then other electrons, as they try to go through may be a structure of the material which may be crystallic, all right? It feels the need to spend energy to go through. And as the electron spends energy, what does it really happen? You see an increase of heat locally. So the energy that the electron needs to spend to overcome the barriers that come from the structure of the material, all of this turns into heat. Therefore, the more of these electrons you have that try to escape on the, because there was a voltage that applied, because there is an electric field that was placed on, it was exerted on this material, the more of these electrons try to leave, the more energy you lose. And therefore, the more of these electrons that you have, the more resistance you have, which eventually, as you know from circuits, resistance tells you what? That you lose energy as the current goes through, and this energy turns into what? Into heat primarily. All right? You remember what resistors do in a circuit. One of the major things a resistor does in the circuit, and sometimes this is very unwanted, is that it reduces your power. Now we place resistors because sometimes resistors are important, as you will see from capacitor from RC circuits. Resistors are important because they provide a time constant for the capacitor to start offloading its charge. You will see that in some other classes. But also resistors are in circuits because just the elements we have in those circuits lose energy. All right, so a resistive element is not necessarily an element that we like to have. Sometimes we put it there because it helps us with the circuit design, but too many resistors practically say that we are losing too much power in the circuit. So in any design, you try to minimize them. But in any case, going to your colleague, sometimes many people define now yet another rho, like this, Greek rho, which is 1 over sigma. And it's called the resistivity of the material. And it's inverse, of course, to this number that shows how many of these electrons we have that move. All right, one important thing, and that's going to be the last thing that I wanted to remind you, is that there is one very important condition that we have as we move from any other material or any other part of the circuit into a conducting circuit. All right, so how to show that? If this is a very simplistic view of what I had before, and then so you have here a current I, all right, that flows out here. Practically, you will assume that whatever happens here with your J sub S, which already I implemented it without saying it, is that the total current here has to be the same with I, which means that there is a continuity of the current at this node. All right? There is a continuity of the current at this node, because otherwise you would lose current. And by losing current, you mean that you lose charge. But you cannot generate out of nothing, and you cannot destroy charge, all right, either. So charges do not disappear and are not generated out of nothing, which means that eventually the currents at different nodes have to be continuous. And that is important in the following simple example, and that's going to be the end of this session. Okay? If we had two materials like this, let's assume that you have two resistors. All right, one resistor is like this, and the other is like that, R1, R2. What is the fundamental assumption you make about the current that goes through? It's continuous, all right? The voltages across are different, but the currents that go through are continuous. Okay, how about if now I materialize those resistors as two blocks of two different resistive elements? All right, so this is going to be, J is going to give JS1, I1, and then of course has sigma 1. And this is going to be JS2, JS2, sigma 2, and I2. And then we have those two, one next to the other, in a circuit form, symbolically like this. What if we are to solve this problem? First of all, we create an electric field, all right? The same way we did before. We put positive charges here, negative charges there. We have JS1 to be sigma 1, E1. We have JS2 to be sigma 2, E2. And what is the boundary condition here? That the total current from here is equal to the total current from there, which means that JS1 times the area should be equal to the JS2 times the area, which means that JS2 has to be equal to the JS1, which means that sigma 1 E1 has to be equal to the sigma 2 E2. Okay? What does that really remind you? It reminds you the electric boundary conditions, all right? The boundary conditions on a dielectric interface, where what is equal through the interface? The normal component of what? Of the electric flux density. And so practically what we had there was the product of epsilon 1 with the electric field had to be equal with the product of epsilon 2 with the electric field. In this particular case, we don't have epsilon, we don't have dielectrics, we have conducting materials, but the property is the same. All right? And what would happen if they were like this? And we had JS1, E1, sigma 1, JS2, sigma 2, E2. What is the boundary condition between these two? E1 goes like this, and E2 goes like that. That the two are tangential. Okay, so the boundary condition between these two conducting materials is that E1 equals E2, which is also very similar to what we've seen in dielectric interfaces, where what is equal through the dielectric interface? The tangential component of the electric field. All right, so this is the material we've had so far. And to look at the time here. Okay. What I would like to do is to give you now, and then thank you. Oh, thank you. Yes. Thank you so much. Yeah, can you, these are group problems, yeah. So give to everybody one.
All of them are group?
Yeah. Except of this. Yeah, all of them are group. And then I have put at the, yeah, so we'll, which one? And I can also do this one on the other side. You know, take one side and I will do, yeah. I will do the other. 1, 2. That's okay. That's okay. What? That's possible. He did not show.
How do we do that?
He's your group leader.
Yeah.
Okay, you assume, one of you assumes the role, and you tell me.
Okay.
Yeah. All right, you just tell me.
Right. Thank you.
Yeah, thank you. Okay, now, what is one thing you need to remember when you are to take an exam? You have to read it well. All right, take your time to read it. From the moment I stop talking, you're going to have half an hour. So I'm not taking any part of your time. I just wanted to take you through the problem, all right? To make sure that it's, so 100 points for the group problem, 100 points for the individual. It's one problem. It's a ideal parallel plate capacitor, but the only difference that this capacitor has from all other ones that we've solved is that the plate is not a rectangular plate, it is a circular plate. That's the only difference. Everything else is the same. And I then give you the positive charge, the negative charge. Now, unfortunately, on this picture, because the positive charge was supposed to look on the other side, but when we made the copies, it shows like it's on top. But I was able to explain that the positive charge is equally distributed on the inner surface of that conductor. The negative charge also is equally distributed on the inner surface of the other conductor. All right, so they face each other. I give you the values of Q, of the radius of the circular areas, and also of the distance between the two parallel plates. And first, I ask you to find the electric field intensity in between the two plates and along the axis of the capacitor. The axis, you know, that it goes through. The axis, I don't know whether you need me to explain more. Is it clear what axis is the one? I mean, as the capacitor is like this. Make sure that we don't. Capacitor is like this. This is the axis, okay, of the capacitor. Then I ask you to tell me, if you find this, what will be the value here? Remember, this is an ideal capacitor. We've talked about ideal capacitors multiple times, right? I just want to make sure that you remember that. That's why I'm asking you. And then I want you to find the potential difference between points 1 and 2. All right. The next one, part 2. I tell you that the points 1 and 2 are connected to a voltage source of 8 millivolts. And I want you to find the new total charge density of the capacitor, and then find the capacitance. And then, assuming that the two plates, everything else remains the same. So the 8 millivolts, the charge, the capacitance, the charge, assuming that the two plates are brought closer to each other by 20% of its original distance, of their original distance, what happens to the capacitance C? So you assume the same Q, you assume the same voltage, and then you just bring them closer. All right? And you find out what happens to the capacitance, assuming that the voltage is 8 millivolts. Then we go to part 3. The same capacitor, what I do is I put a dielectric, like a rod, in the middle of it. And the dielectric is like a cylinder that has a radius of 5 millimeters and has a dielectric constant, epsilon, relative dielectric constant, epsilon sub r of 4. How now, I would like to ask you how the charge redistributes on the capacitor plates. And just do a very brief, plot. Second, find the voltage difference between points 1 and 2. find the capacitance and compare this capacitance to the value that the capacitance would have otherwise without the dielectric. All right, you assume that Q is given, A is given, H is given. The radius of the inner dielectric rod is given, and the relative dielectric constant. Any questions on this? Yes.
So we're only going to write on one piece of paper?
Yes, for the group, but each one of you has your own. And you can speak freely. Yes?
The group 2 is here.
Can you guys move and meet your colleague who cannot come downstairs? Yeah, there are chairs. I think you should probably do that because your colleague cannot come here. Yes. Okay. Okay, and you can have, so, thank you very much. So you have half an hour from now. All right, now is what time?
So we should choose one to do the actual work on capacitor and first.
2:52. Oh, thank you. So, Okay, as you're collecting your material, here is how I know you need a break, but what we're going to do is the following. I'm going to distribute to you the individual group. Then you will take a break. I will explain to you because I need to go to the airport and pick up, and I have to go out of town tonight, and we'll come back tomorrow for a meeting. But I then explain to you what the individual is, that you will take a break. You are going to be here at 3:32 something, and then you're going to have until 4. All right? So I'm distributing the individual ones. Don't try to go and start solving equations. I mean, like for electric field, I told you I don't want you to solve for the electric field. All right? So you remember that. I can put it in multiple places. So you have a capacitor here again, but the inner conductor is like an electric conducting rod in the middle. All right? I have two views of that. And the outside is a metallic cylinder. The capacitor, it has multiple materials, four, the way it's there, inside between the two conductors, and has a length of L. And of course, it has a positive charge Q on the external cylinder, its inner surface. It has a negative charge Q on the internal cylinder, and of course distributed on its inner surface. And then I give you the total Q, I give you the radius A of the inner conductor, I give you the radius B of the outer conductor, and the length L. And I say, without explicitly solving for the electric field, find the total charge on each quarter of the surface of the internal conductor. You see the internal conductor, how it is divided in 4 quarters? All right, the 4 quarters here on the first picture. The internal conductor is divided on 4 quarters. All right, I want you to find the field, the total charge that is distributed on the quarter surface of each one of those, all right? So each of these quarters, of course, has 1/4 of the surface of the cylinder. And then of course, after you find the charge, I want you to find the capacitance. And then you assume that in the previous capacitor you take away all of the dielectrics and you fill it with air. And I want you to find the new capacitance also without solving explicitly for the electric field. And the last bullet is that if you want to keep this capacitance for part 2 the same as the one in part 1, which you have already calculated, what is the value of length L you will need to choose to achieve this goal? Okay? Think about this, how to do it. Don't try to throw everything on the page because it's very simple. So if you see yourself, don't try, think about it, how to do it. I told you that you don't need to know the explicit value of the electric field. So that should give you a hint. Okay? As I said, I will have to leave right now, but Angela will be able to respond to your questions, and then you have until 4 o'clock, excuse me, to finish. And it's like, you can take a break in between if you want. That's not a problem, all right? So if you wanna, and then if you wanna take a break for 5 minutes for some reason, then you please tell Angela and you can stay 5 minutes longer. All right, your break should not really create a problem for you in doing the solution.